हाँ, स्लाइड को प्रेजेंट हाँ हाँ स्लाइड प्रेजेंट हाँ हाँ
A warm good morning to one and all. Welcome you all to the second day of this session, STEM 2023. Today's session will be taken by Professor Arnab Ghosh from NIT Rourkela on the topic Design of Switching Converters and Power Management for Microgrid. Professor Arnab Ghosh received the BTech and MTech degree from West Bengal University of Technology, Kolkata, India in 2010 and 2012 respectively, and the PhD degree from the National Institute of Technology, Durgapur, India in 2017, all in electrical engineering. He is currently an assistant professor in the Department of Electrical Engineering, National Institute of Technology, Rourkela, India. His research interests include the design of power electronics converters, renewable energy sources, microgrid and smart grids, electric vehicles, and vehicle-to-grid applications. Now I welcome Professor Arnab Ghosh, sir, to deliver his lectures. It is over to you, sir.
okay. Oh. Okay, very good morning to all the participants. Okay, so thank you for giving my brief introduction. So I think I am audible from the participants end. Hello.
Yes, sir, you are
Yes, sir.
audible.
Yes, sir.
Okay, thank you.
Audible, sir.
Okay, so actually I am Arnab going to deliver about our presentations that the design of switching converters and the power managements for the microgrid application. So before starting of that sessions means it's an informative session. Okay, so we need to know what is the basic motivations for introducing this kind of topic for this present for these courses. Okay, so we can understand that our course title that is sustainable technologies for the energy management of hybrid microgrid system. So if we are introducing the sustainable sources for our system, so most important part is that integrations of that renewables to our network. Okay, it can be hybrid network or any kind of network. Okay, so if we want to introduce the renewables to our network, so definitely we have to design some specific converters for interconnecting those sources to our grid. It can be the standalone grid, it can be grid connected conditions also. So before starting of the session, so we need to know about the what is the basic motivations for this. We can see the most important part. There are two important parts are there. One is switching converter. Okay, so there is one important part, that is our switching converter. Okay, another important part is the power management. So first, what is the motivations for this switching converter? So why it is important and how we are going to implement them. Okay, so what is switching converter? Basically, we are integrating the renewables to our system. So we have to design such type of converters that can directly connecting your renewables to the to our concerned microgrids. Okay, so all the time we are talking about the microgrids. So what is the basic meaning of the microgrids? Okay, so there is a lot of lectures already completed from yesterday. So I hope you are having some brief idea about the microgrid. Still, I'm having some slides. So based on the some basic idea about the microgrid, sort of the different kinds of microgrid, how it is implemented. Okay, some basic idea we can able to discuss in this presentations. This is the first part, and for that integrating part we need to design some switching converters. So here we are going to discuss how the switching converter will be designed. If it is designed, then how here it is going to be implemented. Okay, and next part is that power management scheme. Okay, so if you are having some renewables, so we are all are aware about that the intermittency is there. So if the intermittency is there, so they are totally unpredictable. Okay, so that's why the reliability issues are the main point of concern. So we have to depend some of the storage system. So how we are going to manage the storage? Some basic examples, some basic simulations we are going to discuss as well as demonstrate over here for the better understanding. So these 2 points we are covering over here: the switching converter design as well as some basic idea about the power management. Okay, so then we can able to see, so what are the most important points why we are going to go for the sustainable technologies. What are the main point of concern? So you can see day by day we are giving more trust how the utilizations, okay, how the energy utilizations are affecting to our system. So if we able to see that initial days we are designing the power plant that are nearer to our base load. Base load means, suppose if you see in that first kind of power plant installed in our India, that is British government time. So they have installed those power plant where the industrializations as well as the community or colony area of those related of that industrial belt. So that's why the concept is coming the base load conditions. And now we are designing the power plants. It's not about the base load. You can connect any kind of places. After that, that total power will be transferred to the grid. Okay, and you can utilize that energy in different point of our country. Okay, so it's not the totally conventional power plant. Sometimes the renewables also been integrated with those power plants. Okay, so the energy utilization is another important factor. So what are the most important factors for the motivation? There is a agreement. There is an agreement in Paris Agreement. By that agreement, India took the oath that by 2030, so they are going to reduce that overall 2 degree temperature of our nature. Okay, of our environment. So for that one, so they are taking some plan of actions. Okay, national action plan. So how to they can reduce the emissions of the greenhouse effect as well as that they can countering the effect of global warming. Okay, so that's why you can able to see some of the important identified sectors. Okay, sectors identified under the climate change agenda. So first point is that they are shifting about the more utilizations of the renewables. Okay, so renewables, they are already integrating with our system. If we are traveling any of the place, we can able to see some railway stations, the rooftop solar photovoltaic, as well as government also promoting to install the solar photovoltaic in your in-house applications. Okay, so the government dependency of your conventional energy, so you can generate from your own sources or own resources in your in-house. Okay, so this is one of the important factor, that is renewables utilizations of. Next point is that how you are this is your generating part. Okay, next point is that how you are going to utilize them. Okay, so utilize them means, now most point, if you are able to see some example, that we are able to see that utilizations of the energy means, in our early days we are using some different vapor lamps. Okay, fluorescent lamp. After that tungsten filament lamp, then the concept of the illumination especially. So gradually their energy consumptions in more than 100 watt, nearer to sometimes 500 watt. Now it is reduced to, you can able to see that we are using LED lamp for the lighting purpose. Their normal wattage, whatever we are using our domestic application, it is 9 watts. So there is a huge changing of that energy utilizations. That is another important factor. Now the transportations, e-mobility. Okay, so this is important issues for that purpose. Another important issue, the conservations of your natural resources like water, forest, then the waste management. Okay, so another point of concern is your waste management. So how it is important? Basically, we are talking about, all are talking about some heavy metal, means storage reliability factors. So we are talking about some different lithium ion batteries, lead acid batteries, so different kind of ion batteries we are talking about. So most of them are related to the heavy metals. They are concerning the heavy metals, consisting of the heavy metals. So if we directly drainage them, because of that it's having some cycle, it having some life cycle. Okay, so if we drainage them directly to that conventional field, so it can cause for that pollutions. Okay, that's why the waste management is another important factors. Okay, finally we are utilizing in the building power management. Okay, now we are talking about giving more trust on that standalone microgrid systems. Okay, standalone microgrid system means we are talking about we are generating the power from our own side. So if we are generating, so how we are going to manage them? Suppose you are morning time, suppose morning time you are using solar photovoltaic. Basically, you are charge your battery through the solar photovoltaic. But evening time it is not there. So how to manage them? Okay. So every point of concern. So we are going to trust our focusing our research to such a dimension, so we can controlling them as well as we can utilizing them in the optimal manner. Okay. So these all are the important factors for point of concerns. Okay. So here we can able to see some air pollution index. So if we able to see that in our country, okay, so some important cities we are giving. So that is far mane, uh, you can able to see that is their pollution index is more than any renowned cities of our neighbor country China. Okay, so that's why we have to think about how we are going to reduce the pollutions and all those things. So here we can able to see some typical structures of the microgrid. So these slides are consist of some basic ideas about some different topologies of the microgrid. What kind of microgrids normally available in our country as well as extended to other countries. So we are talking about over here. Okay, so here we can able to see the structures of the microgrid. So what are the most important factors, common factors for that microgrid? So we can able to see some of the sources. Okay, the sources can be the renewable sources like solar photovoltaic, wind. Okay, as well as some conventional sources, means power plant can also be connected to your system if it is in working in the normally it is a standalone condition. So there is a circuit breaker. Okay, so if we are going to change it to the grid connected mode, then this source will be connecting to your microgrid. So if it is connected over there, so it's having some own generations. Okay, so from the generation will coming from solar photovoltaic and wind, and you are able to see some battery storage also be there that can provide you the reliability of the system as well as some EV or any kind of charging stations are there. And who is taking care about all those concepts? Who is taking care about all those controlling method? That will be taken care by the monitoring system. One monitoring system is there. Here you can able to see that energy demand, three important factor: monitoring the system, controlling the system, and the balancing the system. Okay, so basically why the monitoring is required? Suppose we are having, normally we are talking about, we are working on that standalone condition. So suddenly the situation has arisen such a way, so the generation is less than your demand. Okay, then what happened? So if your system is not sufficient to provide that amount of energy, directly system can be collapsed. Okay, so that's why we have to monitor regularly, and we have to take the data and regular manner. So so we can predict the demand of the system for season wise as well as the day wise as per the requirement, and based on the data we can generate some algorithm so that can control the overall system efficiency. Means we are talking about different kind of switching converter, different kind of converters are there. So they are controlling based on your demand. Okay, so based on the demand, so you know there is a important factor, the storage. You can able to see the storage play the important factor for transferring the power if the demand is more than your generations. Okay, so if so we have to integrate some of the switching converter that directly connected with your storage and the system. Means you can talking about the local grid or local bus. Okay, so power will be transferred from your storage to your bus. Okay, so we can able to stabilize the system. Okay, so and we can maintaining the balance. Okay, that's why these three part is very important: monitoring, control, and the balancing of the system. Okay, so here we can able to see the radial structure of our microgrid. Okay, now this slide consists of some we can say like that definitions of our electrical grid, synchronous grid. Okay, so microgrid. Okay, so we can go for the next point, that is for the classifications of the microgrid. Okay, so microgrid can be broadly classified in the different 5 parts. Here you can able to see the mode of operations, first part, then type. Okay, so in the mode of operations, microgrid can be working in that isolated mode or grid connected mode. Isolated mode means it's not dependent on the different your conventional grid. It can work standalone condition. So that is your isolated condition. Another one is the grid connected condition. Means any emergency situation happened or somehow it can directly connect it to the grid. It's coming from your isolated mode to the grid connected mode for mitigating the energy demand. Okay, then type of microgrid also be there. Based on the type, it can be the AC microgrid, DC microgrid, and hybrid microgrids. Okay, so we are giving more thrust on this part of that. In this lecture, we are giving more thrust on this part of the microgrid. Why? Because of that, in this part, we are going to discuss about different types of converter, what kind of converters are using for that applications, and if the converters are using, how we are going to design them. Okay, and what are the different methodology to design them. Okay, so this is your type of converter. Okay, sorry, type of microgrid, AC, DC, maybe hybrid. Okay, and then we can able to know the based on the source. Microgrid also been segregated 3 types based on the only renewables. Okay, the source is based on your only renewables. Next one is your diesel, means fossil fuel base. Okay, and the hybrid means both your renewables and the fossil fuels both are present in the hybrid microgrids. Okay, in the renewables it can be solar, it can be wind, it can be pico hydro or the smaller hydro, biomass, or hybrid, means all can be consist of there. Okay, now one point is that what is clean energy and what is green energy. Okay, so clean energy means green energy means directly it is energy that is environment friendly. Okay, clean energy means it's not totally environment friendly. Nuclear energy is there, it's an example for the clean energy. But renewables, those are there, suppose solar, photovoltaic, hydro, they are in green energy, means there is no adverse effect to our environment. Okay, so here based on the scenario based, we can able to segregate that residential, industrial, and commercial. So 3 types we can able to separate them, and finally based on the site, means based on your load demand. So it can be less than 10 kilowatt or 10 to 1 megawatt or maximum more than 1 megawatt. So where our main point of concern is the different types of microgrid and what type of converters are associated with this microgrid study. So we are talking about the microgrid, means microgrid concept. Now it is very famous, but it's not a new topic. Okay, so in India, first 1980s, so first microgrid was installed in our Ganga Sagar. Okay, so in that field, so that was diesel generator based microgrid. So now we are talking about the microgrid only for our base generation. So means nearer of your locality, and from that place we are directly get our we can get our energy from our resources. Okay, so in case of DC microgrid, whatever sources you have, we are having some example for renewable energy. Suppose PV, you are taking example from the PV and the wind. Okay, so both are connected to that DC bus. Okay, so this bus you are able to see, this one, this bus, this is your DC bus. Okay, so whatever generations are there, like you are converting to the DC. Suppose you are having PV, so output of the PV is coming in DC, so that is directly converted, that directly controlled by the DC-DC converter and fed to your DC bus. Okay, here we are able to see the wind, the output of the wind is coming AC, so directly it is converting to the AC to DC and feed to the DC bus. Okay, so whatever generation you have, you are directly connecting to the bus, that is DC. That's why it's an example for a DC microgrid. Okay, here you, if you want to connect any kind of AC module supply or okay AC supply to the system, that also been converted. You can say like that. You can say like that grid connected conditions. Okay, so directly single phase AC you can connecting to the microgrid through a AC DC convert. Okay, so directly it is there, it is converting to the DC. Okay, so here another important part you are able to see, that is your storage module. Okay, so in this phase, why the storage module is important. Okay, so before going to discuss on that, we can able to see some different loads are there. It can be AC load, it can be DC load, it can be DC load, whatever loads are there based on our requirement. Our requirement is DC, means our requirement is we are having the sources is DC and requirement can be the AC, can be the DC. So based on our requirement, we are converting from DC to AC or DC to DC or DC to DC based on our requirement. What kind of loads are there, we are going to drive them. Okay, so now most important part is our, that is storage module. Okay, so here suppose that loads, we can able to see the output load, suddenly the the load demand is more. Okay, compared to your generations. Okay, so compared to your generation, then what happens? If load demand is more, so additional energy from where it will circulate it. Okay, additional energy will come from your storage to your storage to your load. Okay, so in case of storage, what kind of storage you are using? Battery, capacitor. Another storage you can able to see over here, that is electric vehicle. Why the electric vehicle is used just like a storage? Okay, I am coming that point. So normally we are using for the battery and the super capacitor or the ultra capacitor. Okay, for ultra capacitor normally used for the initial transient condition due to high power density, and that is for the high energy density. Okay, for the steady state. So both can be hybridized. Now point is that why the electric vehicle is written over here. Okay, so if you are able to see, suppose we are taking an example. Okay, in our domestic applications. Okay, what is the peak demand? Okay, what is the timing of our peak demand? So normally we can able to see that evening time. Okay, evening time. Okay, so we are busy with lot of domestic works. Okay, so that's why the energy or power demand, you can say like that, that is more. Okay, so from where that additional energy will come? Normally EV is connecting, or you can say like that EV batteries are charging through your grid. Okay, means domestic grid. Okay, so that you can set such a manner. So evening time, for the durations, that additional power, that whatever power is stored in your EV batteries, that can also be transferred. Okay, or that can also be mitigating the demand of your demand of your requirements. Okay, sorry, that can also mitigating the requirements. Okay, so that battery can be used for some durations. After that, it can be charged. So what kind of charger is required for that one? That is DC-DC bidirectional chargers are required. Okay, here we can able to see that both the cases DC-DC bidirectional DC-DC bidirectional converters are there. They can charge or discharge your battery. So similar kind of converter also be there, that is DC-DC bidirectional charger. Okay, so these all are the basic layout of your DC microgrid system. Okay, now we are talking about AC microgrid. So whatever sources you have, okay, so whatever sources, what is the problem with the DC microgrid? So if you are able to see the comparison, there are loss comparison is more in your DC microgrid. Okay, that's why we are going to switch to the AC microgrid. But problem is that in AC microgrid, okay, so whatever sources you have, PV, wind, okay, or energy storage, normally we are using DC-DC converter, DC-DC bidirectional converter. For that bidirectional power flow from the energy storage to your DC bus or AC bus. Now you are using some special type of converter, that is AC, that is DC AC. Means it is a bidirectional inverter. Okay, so bidirectional inverter. So you can convert whatever sources are there. You can able to see the output is coming AC. So if all the outputs are coming in AC, then main problem is that there is a chances for the frequency mismatching problem. So you have to design such a way the ripple factor should be same. Otherwise, the synchronization issues may come. Okay, if it is there, so no issue on that way. And you can able to see whatever load you have, DC load or AC load, whatever load you are converting, you are designing the converter such a way. So AC DC converted, so driving to the DC load, or AC converter to driving to the AC load. Okay, so based on your requirement, and you are converting to all the power sources, all those things in the AC bus. But instead of if you are using DC bus, so whatever sources you have, you are converting to the DC. Okay, basically your bus is DC, that's why you are converting to the DC. Okay, this is your example for the DC microgrid. So here we are able to see the difference between the AC microgrid as well as DC microgrid. So both the way. Okay, now we are talking about the hybrid microgrid. So if the unnecessary conversions are there, some of the places, okay, if you are designed such a way microgrid, okay, if you are designed the so if you are designed the microgrid such a way, so both AC DC, both the sources you can connect it to your system. That is a good options or good feasible options for the system. So here we can able to see the structure of the hybrid microgrid. Here you can able to see the architecture or architecture design for the new AC/DC hybrid microgrid. Okay, so you can able to see you are having two bus, one is AC bus, another one is DC bus. Okay, so whatever AC contents are there, okay, AC sources, you can able to see whatever AC sources, like here you can able to see the diesel generator, okay, or that wind, okay, all those cases the output is coming, or if you are having biomass gasifier, or you are having picohydral, whatever things are there, the output is coming as an AC. Okay, so you are connecting those sources in your AC bus here. Those sources you are in AC bus, the diesel generator or wind power, your output is coming AC. Okay, as well as you are connecting the AC load over here. And if required the grid connected condition, grid can also be connected through the circuit breaker, it's a transformer, to your AC bus. Okay, and in case of DC, what happened? You are using battery, solar photovoltaic battery. Okay, all those DC thing, it's coming connecting over there. Okay, now the bidirection based on the requirement of your load. Here you are able to see that it is your AC load. Okay, as well as you can able to see the DC load. So based on your requirement of your demand, the bidirectional power can be transformed from your AC bus to DC bus, as well as DC bus to AC bus. So bidirectional power can be transformed through that converter, that is AC DC bidirectional converter. Okay, so we can able to see one main converter, another one is auxiliary converter or backup converter. If you are taking shutdown of this converter, so this converter can be used on that. So this is the basic structure of your hybrid microgrid. Okay, so now we are giving more trust on that hybrid microgrid. Now what is the function of the power electronics converter for that interfacing module? So whatever structure we are able to see over here, so all those cases we can able to see what are the different types of converter we are using. First we are using that interfacing purpose. Okay, that is your interfacing converter. Suppose you want to connect the solar photovoltaic to your DC grid. So directly you cannot connecting directly the solar photovoltaic to the DC grid. You have to connect to one DC-DC converter for interfacing purpose, and you can connect. If you want to use some wind, so directly you cannot connect that wind output of the wind power to your bus. So in between of them, one converter is required. Okay, so it's your interfacing purpose is using. So those converters are known as interfacing converter. Another converter also be there, that basically that converter is maintaining. Sometimes what happen, if you want to stabilize the voltage, okay, so you have to design the converter that can maintaining the characteristics. Suppose suddenly changing of your load, so mitigating the load demand. So as per the controlling of your switching pulses, okay, the converter can be controlled. Okay, so that is also another converter you can able to use for maintaining the phase frequency, means for the another purpose. Final one is your bidirectional converter. Okay, so bidirectional converter, you can see there are different kind of bidirectional converter. It can be the DC-DC bidirectional converter, or it's a DC-AC or interlinking converter. Okay, so different kind of converter we are able to see over here. But problem is that if you are using different kind of converter, so there is a high chances for that power quality issues. So whatever converter you have designed, so you have to maintaining that it following the protocols or not. Okay, so that protocol should be maintained. We have mentioned some different kind of protocols, okay, or standardizations for these applications. Okay, it is directly taking from the references, so you have to maintain the protocols, okay, for the power quality issues. Now we can able to see several kind of converters, so we have to find out what are the topology of the converter, then mathematical modeling, control scheme, and the implementation. What is the significance of this slide? Main point is that, so we are having several kind of converters. So we cannot take X, Y, Z any kind of converter. Suppose we are taking some DC-DC converter examples, buck converter. Okay, that is also another DC-DC converter, boost converter, buck boost converter, SEPI converter. Different kind of converters are available in the literature. So which one we are going to be used based on our requirement? Okay, what is the meaning of that? Based on our requirement. Okay, so that's why the topology selections are required. Okay. Suppose in case of interfacing purpose, okay, we can use that boost converter as well as buck converter also. Okay, sometimes we can able to use such topology such a way, so both buck boost possibilities are there based on a requirement. Based on the requirement, we have to select the topology of the converter. Okay, so this is the first part. Then what we are talking about in the first microgrid structure, okay, we are talking about the monitoring, control, and the balancing of the system, means stability of the system. So monitoring means whatever parameter, whatever values, means requirement of the power demand, whatever the values we are collecting for every instant, okay, and fetching those data in our local server, maybe the global server. Now you know that app-based control, IoT, okay, different kind of advanced control or smart control technique, not advanced control. These all are the examples for the smart control technique. So we are talking about big data handling method. So you can able to get all those values if you are retrieving the data. So huge data will be there. So you have to handle them. Okay, so that's why whatever topology we are going to select, then we have to control or we have to response. Okay, we have to response as per our requirement. Okay, and after topology selections, next point is that we have to design the controllers. Okay, if we are going to design the controller, so controller is the total mathematical approaches. Okay, control is the total mathematical approaches for the practical implementations. Okay, so that's why we have to selecting such a method that can represent our power electronics converters all are physical system, so that can convert the physical system in the accurately in the mathematical model. If the accuracy is not there, so the result will be the
କିଛି ଥିଲା ଠିକ ରେ ଏତେ ସବୁ ଇକ୍ୱେସନ ଥିଲା ମୁଁ ଜଣା ନାହିଁ ତ ଲାଷ୍ଟ ସେମିତି କରି କରିକି ବାହାର କରନ୍ତି କଣ୍ଟ୍ରୋଲର ତ ଡିଫରେନ୍ସ ସେ କହିଲେ
okay, so we can design the converter topology such a mathematical manner, so it can so it can accurately replicate it, and after that we can use the control law to that based on that mathematical part. Then what we will do? Then we are using implementing software. Then we are using some software for the whatever idea we are using over there to study in our software for the implementations. Okay, implementations can be first computational analysis, or you can say like that in software platform we are using, it can be NI multisim, it can be any XYZ, MATLAB, okay, any other software also. Finally, the experimental implementations. Okay, so this is the flowchart for how we are designing, how the topology will be selected, and the mathematical modeling, finally control designing, and the implementation purpose. Okay, so what are the most important prerequisite after the designing of the converter? What are the expectations from the from your overall converter as well as the control? First one is that good line regulations. Okay. Second is your load regulation. Finally, transient response, and is it stable or unstable system. Okay. So line regulations means how any kind of disturbances are there. Okay, in your input side. So converter should be controlled such a manner, but such a manner that output should be maintained. Oh, it should be constant. Okay, nearer. But it's not that more than 5%. So it is 1% also very high, but if we cannot go beyond 5%, so abruptly that results can be changed. So that can changes the that can changes your goes tends to the instability issues also. So next point is the load regulation, mean whatever disturbances in your load side that can also be regulated. Output, whatever outputs are there, okay, it should be regulated. Means what is your output? Normally, as in we are talking about the load. Load means in as an electrical point of view, load means we know that's current. Suppose your normally whatever system we have designed, so power should be maintained or power should be constant, both input as well as output. Suddenly your load is more means load current is more. So if you maintaining the power means your voltage. Okay, so power is constant. So if current is more, so voltage should be dipping or reducing. So whatever converter you have, so it can be adjusted. Okay, their control logic will be such a way it can be adjusted the control logic and the pulse width of the system, and it can maintaining the proper regulations. And finally, the good transient response. Okay, so response time. Okay, means how fast system is behaving. Okay, it totally depends on your control topology. What is the control structure you are using over here that can be maintained over here. So transient response. And the finally we will be talking about the stability. Okay. So if all those processes been maintained, then automatically the system will be stable. Sorry. So here we are discussing about what are the different modeling structures. So okay, so we know that power electronics converter and as a switching converter. So they are highly non-linear. What kind of non-linearity is there? That is called switching non-linearity. Means on off like that. Periodically it is turned on, turn off. So switching non-linearity is there. So that's why we are using some state phase averaging method for linearizing the time variant, non-linear time variant system to the LTI, linear to the LTI system. Okay, so linear time invariant system. Okay, so there are some steps are there. So 4 steps are there. First step, what we are writing? We are writing the differential equation based on our state variables. Okay, so we have to identify what are the state variables are available. Okay, means based on your energy storing elements. Okay, suppose you are using capacitor, inductor. Okay, number of capacitor, inductor. You are selecting that you can identify the number of state. Okay, based that is we know the state variable minimal number of variable that can define the state of the system. Okay, so in this case, if we are using some very basic converter like buck converter, boost converter, so we are using normally one inductor, one capacitor. So it's a second order system. 2 state variables are there: inductor current and the capacitor voltage. So based on that switch on condition and switch off condition, we are designing the we are writing the differential equations. Okay, so it's your state equations and both are the output equation for both of the state. Okay, after that what happened? We are going to average them. What kind of averaging? It is duty weighted averaging. Here we are averaging, actually there is a DTS, means switching time, but we all are divided by, total thing is total divided by TSW, means all those things the TS are there. Okay, so divided by, so time variant. Okay, so we are duty weighted. Okay, we are going to average them. After that what happened? We are doing for perturbation, small AC perturbations, whatever state variables, you can able to see the variables, that is one of the variable, these variables, all the variables can be replaced or it can be perturbated two way. One is AC, this is your AC factor, ripple, okay, another one is constant DC. We are perturbating such a and replacing to your equations. After replacing that equation, so we'll get some identity. Okay, from that identity we are separating the DC part as well as separating the AC part. After separating the DC part, we'll get the steady state DC voltage transfer function, or you can say like that gain kind of thing. Okay, DC gain. Okay, and separating the AC part, what happened? We are getting some expressions and some
It's not audible. Sir, it's not audible. Sir, it is not audible.
Kindly check the audio, sir.
Sir, last 2-3 minutes, 3-4 minutes, it is not. We can't hear anything. No, screen is visible, but it's not audible. Dr. Ghosh? Dr. Arnab Ghosh?
ঠিক আছে। So here we are able to see Red color is the This is the basic block diagram of a switching converter. Now we are talking about the interfacing purpose. These kinds of converters. ये नीचे ये क्यों है? Okay. ठीक है.
Sir, actually, we have missed the slide three, that step 3 as well, because during that time audio was missing.
Step 3. This one. Hello.
Yes, sir. Yes, sir. From here onwards, you can continue.
Okay. So in step 3, we are discussing about the perturbations. Okay. So whatever variable we have, state variable. So we are perturbating the state variable into two parts. This is your DC part. Another one is the ripple part. Okay, small AC part. Okay. So overall, throughout that parameters, it will be variables. It is be perturbating. After that, what happened? We are getting the identity. Okay. The AC as well as now we are separating the AC one as well as the DC one. So from the DC one we are getting the steady state DC voltage. Okay, over there. This is our steady state gain we will get from the DC after separating the DC, and for the AC what we will get? We are after Laplace transfer function, after Laplace transformations, then inverse Laplace transformation, we will get the Planck transfer function of that converter. Okay, here we are able to see the closed loop block diagram of the switching converters. Okay, so from where we are, this is how it will be operated. Okay, so we are sensing the output voltage over there. Then this output voltage will be comparing with your reference signal. Okay, after that we will get the error signal. Okay, normal situations, if there is no load disturbance, means the load means is an electrical point of view. So more current. Okay, so due to load disturbance, so voltage may be dipping over there. Okay, so error will be more. So you have to fix up the logic such a way. So for the due to the dipping of the voltage, the turn on time or time T on of the switching converter should be more to mitigate that problem. Okay, this is the basic idea for the closed loop block diagram of the switching converter. Okay, after that, this kind of switching converter normally using for or interfacing purpose. So we are taking some examples for the solar photovoltaic, where we can able to see some panels are there. From there, you are taking the parameters like panel current as well as panel voltage that is passing through your MPPT algorithm. That algorithm is controlling the pulse width or gate pulse of your DC-DC converter. Okay, so directly it is controlling the DC-DC converter. Okay, so this is a feed-forward kind of control. Okay, here we can able to see, we have to find out different algorithm can be used for that MPP purpose, or find out the maximum power point purpose. Here we are able to see. Okay, so it's a basic structure. If you are having one solar photovoltaic, then one DC-DC converter is there that can be controlled by the MPPT algorithm and feed to your DC bus. Okay, and the DC bus can also be used for different purpose, for the bidirectional fast charging purpose, and it can be also using for the connecting to the grid also. Okay, and overall the controllers are there that can giving the pulses. Okay, giving the pulses for all kind of converters. Okay, so this is the very basic diagram. Now we are talking about different state phase average modeling for the some converter like boost converter, buck boost converter. Okay, so the basic process we have already followed. Whatever mathematical expressions are there, we have already discussed. Now we are directly writing the expressions. Here we are having the state equations. Okay, so this is our state equations. So first we are writing the inductor current state equations by using KVL over here. So this is mode 1 condition, means switch on condition. This is switch off instant. Okay, so again this is for switch off instant and this is for switch on conditions. Okay, now applying the KCL. Okay, after KVL, then applying the KCL, we will also get another state equations. Then we are writing the state equations such a way. This is the expressions of the state equations, and after that, this is for on time condition. This is for on time instant. Okay, now we are using the off time instant. Okay, this is our off time instant. So again we are writing the state equations of inductor current and the capacitor voltage. Okay, after that what we will do, we will write the output equations. Okay, this is for the state equation for uptime. Okay, off conditions. Now we are writing the output expressions. Okay, for on time, this is output expression for off time. This is output expression for on time. Now both of the output expressions can be can be average. Okay, so for the T1 conditions, average throughout the time period, means switching time period. Okay, so this is expressions. Okay, after that we are averaging. Okay, so now after that we are separating them. Okay, this is the expressions for the output voltage. This is the expression for the state variable. Okay, then we are using which method? Perturbations. Okay, after perturbations we are using we are separating the identity, but those steps we are already discussed. So directly we are using the general transfer functions. Okay, so this we are replacing the values of A1, A2, B1, B2, C1, C2, D1, D2 to our general transfer functions. Okay, so control to output transfer function of the plant transfer function. After replacing all those expression, we are able to see that in case of boost converter, we are having one right up plane 0. So here we are able to see that one right up plane is 0. So that's why we are talking, we can say like that boost converter having the issues of non-minimum phase problem. Okay, so what is the meaning of the non-minimum phase system? Means you can able to see as it's a second order system, there are two poles. The pole may consist of, they can contribute minus 90 into 2 means minus 180 degree phase lag, as well as another 0 is in your right up plane. So it can also be contribute another minus 90. So you can, if you plot the phase plot, you can able to see that phase plot it is touching minus 270 degree. Okay, that's why it is called non-minimum phase system, means maximum phase delay system. That issues can be observed in case of boost converter. Okay, so similarly, if you design for the buck boost converter, basically boost and buck boost converter normally using for the DC-DC boost and buck boost converter normally using for the interfacing purpose. Okay, if you able to see the bidirectional converter also, that also been part of that, means you can say like that it can derive from of that buck boost converter. If you want to design the small signal modeling and all those things, finally you will get the transfer function also having such type of problem, non-minimum phase problem. That's why we are having more trust or more conscious about the what kind of controller we are going to design over here. Okay, for the buck boost converter also we are using the same process. Okay, so after utilizing all those equations, okay, we are able to get the control to output transfer function, and this control to output transfer function again we are able to see that one RHP0 is present over here. Okay, so that may cause for another non-minimum phase problem in the buck boost converter. Okay, normally we are using that interfacing converter that having that non-minimum phase problem. So we have to design such type of controller. Okay, that is also known as the type controllers. Okay, it's not a type controller, means it's a special type of controller. Okay, so if you see for the type 2 and type 3. Okay, so in case of type 2 controller, you are able to see one pole is there, that is in origin. Another you can see it's an integral plus a lead type of compensator. Okay, so what is the purpose of the lead type of compensator? Basically, if from this study, due to the non-minimum phase problem, so it can be reach the phase margin or phase plot can touch the minus 270 degrees. So if you are using the lead controller, so it having the capability to phase boost up to plus 90 degree. Okay, that's why there is a chances for compensating some of the phase angle. So for improving the phase margin. Okay, that's why we are using some lead controller. But some steady state issues may be arise. That's why another integral controller is there that can take care about your transient response. So it's a very fast controller. And after that, we can able to design such controller, that is one integral controller cascaded with two lead controllers. Okay, so this can contribute plus 90. This can contribute plus 90 plus a plus 90, means total 180 degree phase boosting capability is there. Okay, so this kind of controller can be designed for that special type of interfacing converter for your for your boost or buck boost converter, and all the derived converter, all the derived structure of your buck boost converter. So all are having the same problem. Choke, SEPIC, JITA, all are having the same problem. So we can use that type of controller for the stabilizing them. Now we are talking about some, here we are having some diagram. Okay, diagram means circuit diagram. Okay, so we are talking about some converter that is called tri-state boost converter. Okay, so topological structure. So some of the cases we are talking about, previous case we cannot eliminate. Okay, we cannot eliminate the non-minimum phase directly. Okay, so we can reduce their effect, but we cannot eliminate their effect. Okay, so that's why we are using such type of another converter that is called tri-state converter. So tri-state boost converter having non-minimum phase problem. So in case of tri-state boost converter, what happened? We are connecting one switch, okay, one switch, MOSFET switch as well as one diode. Okay, so this is connected across of your inductor. Okay, basically if you see some of the literature, you are able to understand. So the basically the non-minimum phase problem is the main point of concern of this inductor. So you have to, what you need to do, you have to discharge, or you can say like that, discharge the inductor energy. If you are able to dissipate that energy, so that problem can be that problem can be you can say like that remove. Okay, so that's why one switch is there, one diode is there, only unidirectional current flow. Otherwise, otherwise reverse case it cannot flow this pathway. Okay, for protection purpose. Okay, so there is a diode with the boost converter. So we are using the structure of the type 3. This structure you are able to see. This is a type 3 structures. Okay, and there is a comparator. Then some logics are there for optical isolator, then typical timer for driving the MOSFET switches. Okay, here we are able to see the steady state waveform. Okay, so for the boost converter, normally we are getting that one positive half, another negative half. This positive half normally coming the difference between your input voltage and the output voltage. Okay, this is normally height is your input voltage. And the negative half normally we are getting from difference between your input voltage minus output voltage. So output voltage is more than your input voltage, that's why it is coming negative. So in tri-state boost, additional one state is there, that is zero state. Any energy is dissipating. So what is the, this is a inductor voltage. This is inductor waveform of steady state inductor voltage, VL. Okay. This is steady state inductor voltage, so VL. Okay, so that's why it is coming like that. So VL is 0, so that's why it is across the voltage is 0, so it's not there. And this is gate passes for the main switch, and that current, inductor current, it is okay. So current is if you using some discontinuous mode of operation, that non-minimum phase problem can be removed. But point is that if we are using discontinuous mode, so the current can be 0. Okay, the overall ripple can be more. So we cannot go for direct discontinuous mode. Okay, in this case some bias voltage is there. Okay, for the magnitude of current also be there. So this is the basic structure of tri-state voltage. There is some overall set of pictures, some other response for changing of inductor current. Okay, this side. Okay. Now we are talking about interleaf boost converter. In case of interleaf boost converter, what happened? Again, the boost converter having non-minimum phase problem. Interleaf boost, if we derive them, it's also having some non-minimum phase problem. Okay, but point is that interleaf boost converter, if you see that waveform, it's okay for inductor current waveform, it is 180-degree phase shift. This is two phase, so 360 by 2. This is 180-degree phase shifting is there. So inductor current are countering each other. So if you see the input ripple, input current ripple is less compared to your normal boost converter. Okay, as well as their dynamics is also fast. Here if you are able to see the step changes of your resistance, additional load changes. So output voltage you are able to see very fast it is changing. Okay, and the gate pulses are there with the type controllers. Okay, but it's also having the issues of non-minimum phase problem. Okay, so finally we can tri-state interleaf boost converter. In case of tri-state interleaf boost converter, what happened? So this converter do not have that non-minimum phase, as well as it don't have that. It also been fast in response. Okay, so we are amalgaming both of the topology, tri-state topology as well as interleaf boost topology. So it is first time introduced. Okay, so that's why this topology is known as tri-state interleaf boost converter. This is the responses are giving over here. for the better understanding. Okay, so here we are talking about now bidirectional converter. So bidirectional converter, you can able to see some structure of the bidirectional converter. This is your battery, this is your DC link voltage. So normally suppose we are considering the DC link voltage is 48 volt. We are considering like that. So you are having the battery voltage is 12 volt. Standard we are keeping. So if you want to discharge the battery, suppose evening time the demand is more. So what happen? You have to try to discharge the battery to your DC bus, okay, or you can say like the DC link. So what you need to do, battery DC link voltage is 48 volt, battery voltage is 12 volt. So you are discharging battery through this converter. So 12 volt to 48 volt. So you need to stepping up. So that converter is working as a boost converter, okay, and reverse thing can possible if your DC link voltage is 48 volt and battery voltage is 12 volt. Okay, if you want to charging the battery. So what happens from DC link voltage to battery voltage, it is charging. So stepping down the voltage. So this is a buck condition. So now you are cascading both of the mode. Money you can say like that coincide both of the method. So you can able to see both the switches can be the bidirectional switch, bidirectional operation like that. So this is a basic structure of that bidirectional buck boost converter with having, you can say like that, only one arm is there. Okay, so it's your buck boost converter topology. Okay, so both of the case. So that we are talking about the non-minimum phase issues. So we can able to study the same for this converter, for the bidirectional converter, for the small signal analysis. So is there any non-minimum issues are there? If there is a issue, so how we are going to control them? Okay, so this is the basic structure. Now some other converter also been available, that is known as hybrid converters. Okay, in hybrid converter, both output DC as well as AC, both kind of output can be possible. Okay, source, the output of the converter can be DC, it can be the AC. Okay, that's why it is known as the hybrid converter. Some structures are given. Okay, then we are going for that some examples. Okay, so we are talking about some bidirectional power flow. Okay, so some bidirectional converters are there. Okay, here you can able to see some two modes of control. Okay, one is, you know, directly it is voltage mode control. You are sensing the output voltage, bus voltage, and reference bus voltage, DC bus voltage. Now your voltage controller you are using voltage control mode for the PWM for controlling the power. So what type of power is changing? So we can able to see some of the examples. So we are having solar photovoltaic system. So this is irradiation level is changing over there. It is your temperature level. So output voltage also be there. So it is using voltage mode control. So red one, so more or less you are getting some constant voltage. If without having voltage mode control, so results are changing. So basic IV characteristics directly taken from the literatures. Okay. Now we are going to simulate that one. Before going for the simulation, where we have already shows this topology two three slides back. Okay, now we are able to see the dual loop control. Okay, voltage loop control as well as the current loop control, and the PWM is there. Okay, so how the S1 and S2 switch will be controlled over there, and the bidirectional power will be changed. Okay, so we are using small signal modeling again. So directly outcome will be written over here. This is your transfer functions. Okay, for the small signal modeling, and this is used for the control design. Okay, two controllers are there. Normally PI controllers are there. Okay, so PI controller we are able to design that KPKI value from there. We are using that as we are getting the transfer function. So it is converted to the linear time invariant LTI system. So we can use the CISO tool in MATLAB for designing that KPKI value for the voltage controller as well as the current controller. And we are able to see that when battery is charging, okay, when battery is charging, the battery current will be negative. You can able to see the negative battery current. It is battery is charging. Okay, after that what happened? Here it is not charging SOC level. Charging means SOC level also been increased. Okay, after that battery is discharging. So battery current is positive and SOC level is reducing. And similarly power is constant. So battery current is gradually from negative to positive side. So voltage also been changing from higher value to quite lower value. Okay. After that we are able to see we are considering one system. Okay, so that is islanded DC microgrid with the solar photovoltaic. Okay, so this is a basic system we are considering. So here we are having some solar photovoltaic, some MPPT algorithm, standard algorithm is used over here. Now main option objective is to study how the power flow has been done. Okay, here PPV means power generated by the PV, P load is load power. Okay, so now different mode conditions we have to see. If your PPV equal to P load means without storage, how system will be behaving. If you are having PPV is greater than of your P load with storage, and now PPV is less than of your P load with storage, and finally PPV is varying, and last three conditions having storage, and one condition is not considering any storage. Okay, then we have to see how it is working. Okay, now here you are able to see that due to the generation, P generation has been changed based on the solar irradiation. Okay, solar irradiance, here you can able to see that PVV, the condition for islanded condition. Okay, PVV is P load, it is considered such a way. So if PPV has changing, okay, so PPV is increasing, so load power gradually it is following the maximum how much load power it can be provided. Okay, so as well as the voltage variations we are able to see over there. Okay, so finally you are getting the power generation from the PPV. Okay, so changing over there. Okay, this is conditions for the buck mode. So PPV is greater than of your P load. Okay, generation is more than your P load. Okay, now additional power, who will take the additional power? Definitely battery will be charged. Okay, so battery power is negative means battery is charging, current is negative. Okay, that's why you can able to see the current is battery power initially is negative for the charging purpose. Load is less. Here you are able to see nearer to 12,000, and you are having that nearer to that 3,000 or 4,000, then it is increased. Okay, like that it is increased finally. Okay, nearer to 10,000. Sorry, nearer to 11,000. It is considered nearer to 11,000, so it is touching to 0. Okay, by that way the second condition it is varying. Then battery power is negative means battery current is charging, so you can able to see initially current is negative, then gradually increasing, and finally it is touching to 0. SOC also been increasing such a way. Okay, with having some slope, finally it is constant, that value. Battery voltage also been reducing. Okay, and finally the voltage variations due to the load using battery we are able to get constant. That's the voltage mode control we are using. For the boost mode condition, PPV is less than of your P load. Okay, so generating power is less than your demand. So additional power should come from your storage. Okay, battery storage. So here we are having the generation. Okay, but you can able to see the load power is more. Okay, it is nearer to 11,000. Here you are able to see nearer to 11,000. Okay, that's why battery power is initially 0. Then what happened? You are increasing the load power, but generation is constant. So what happened? Additional battery power is positive, means battery current is positive, means battery discharging. So SOC level is slope, negative slope will be there. Okay, like that it will be followed through. Here you are able to see battery current is initially 0, then positive, then again more current, so more positive. SOC level is changing such a way. Okay, and this is your voltage variations. Okay, final last mode of operations. So with the variation of irradiance. Previous cases we are not changing the irradiance. Okay, variation was not there. So power generations of solar photovoltaic is there. That is your some power is there. Okay, then what happened? Reducing by changing the irradiance. What happened? The solar generation has been changed. Okay, if it is changed, so load power is making constant up to 10,000. So here it is nearer to less than 10,000. Okay, it is more than 10,000 generation. So somehow some of the portion battery is charging, first condition. Then it is nearer to 10,000, but generation is less. Then what happened? The additional power will come from your storage. So battery current is positive, so battery power also will positive. So voltage will be reduced. So battery current initially charging condition, so negative, then positive. SOC is increasing, then decreasing. Battery voltage also initially charging means it will be higher value, then it goes to lower value. Then voltage variation, voltage is constant. Okay. This is a open loop structure of a bidirectional SEPIC converter. Okay, so one of our students has done all those things. Okay, so some basic structure is given for the open loop system for the bidirectional. Now we were talking about hybrid system. So this work also been done by one of our student. Okay, so here we are having some structure of a bidirectional converter which having battery storage, solar, wind, okay, different converter, whatever topology we have already discussed. Some filters are there. So it is initially we have studied in standalone conditions. Okay, now different conditions we will see how the power management can be done. Okay, so this is the basic circuit model. Okay, so we are having some bidirectional converter, DCC converter. Here battery bank is there. So how it is controlling the bidirectional converter switching. Here you can able to see both of the switch is being controlled and control of the bidirectional DCC converter. Both the converters are there. Both of the switch can be controlled by the logic. This is the basic structure. Okay, for buck mode operations and the boost mode operation. Now we are having some situations, different cases are there. Okay, so this is these cases. From that cases we are having that variable load power demand with the constant generations. Okay, so by you are able to see that generation. So power management diagram flow, power management diagram over here, you are able to see that we are talking about that constant generation. So that you can able to see that we are considering the generation for solar photovoltaic. It is almost constant as well as with the changing of the irradiance as well as the wind. Both are constant. Now what happens? You are changing the load demand. Okay. So if you are changing the load demand based on your requirement. So if this is you are connecting both of them. Okay. So this is your total generation. So additional power can come from your storage. That's why you are able to see that P battery. This is P battery. This is P load. Okay. So additional power due to the changing of the load. So additional power is coming from the battery. Okay. Now second case with constant load power. Okay, with constant load power, the variable solar irradiance. So we are changing the solar irradiance. So this is the pattern of changing the solar irradiance. Okay, so it is telling like the constant load power. This is constant load power. So load power is fixed. Now PV, that PPV value has been changing over there. Wind is constant. So additional, if it is changing, so maintaining it constant, so additional power will come from the P battery. Okay. So the fluctuation, DC link voltage fluctuation with transient also showing over here. This is the next one is that variable solar temperature with the constant load power. Okay, so previous one the changing of the irradiance, now constant temperature. So again it can affect the solar photovoltaic. So overall is same. Okay, with the changing if zoom value is there, how it is changing, but P load is fixed. Okay, and wind power is also fixed. So additional power will come from your battery for maintaining that steady grid DC link voltage. Okay. So next one is that constant load power with that variable wind speed. So here we are able to see that wind speed is varying that point. So that point you are able to focus on the P battery is there, that also change from that point. Okay, and the SOC level plotting also be there. Okay, how it has changed. Last condition, I think this here it is variable wind speed, solar irradiance, solar temperature, and the constant load power. Okay, so all are variable with temperature, irradiance, and the wind speed, and P load is constant. So from where additional power will come? From the P battery. Okay. This is your last case. In last case, variable, all are variable wind speed, solar irradiance, solar temperature, and the variable load power. Okay, load power also variable. So it has also been changed. So these 6 cases are there. Okay, so from where we can understand that how the power management can be done. Some important structure of the controller also be there. Okay, so we are using different kind of power electronics converters. Okay, so for that one we can use some different, you can able to see from the structure. Okay, so here different storage DG are there. The distributed generation can be wind, can be solar, can be energy storage. So all those cases different converters are there. So different kind of controller can be used. So we are talking about here very classical controller. Okay, very classical means normally we are using some voltage mode control as well as classical controllers. Okay, but other controllers can also be used. Suppose you can say like that coordination based control. For that we are talking about the synchronizations in between different DGs. Okay, so for that one, for the coordinations between different DG, so we can go for some coordination based control, graph theory based control. other control can be there. Then most important part is that normally we are talking about different controller, but what are the basic controllers are available in the literature? Okay, so normally we are using decentralized control. So whatever we are discussing over here till now, the examples or applications. Okay, so this is your decentralized control. This means individual converter having individual controls. Okay. And one control is there. What is the benefits of that? Individually you are controlling, but there is no coordination between local controls. So DG means distributed generation, LC means local controllers. Okay, and MGCC means microgrid central controllers. So second point is that centralized control. In centralized control, the local controllers also will control individual DGs for synchronization, but we are using one central control that can coordinate between all the local controllers. But problem is that only one centralized controller, the system will be so complicated. Somehow some issues will arise, so that can replicate it in each and every steps of your system. So entire system should be hampered. So that's why what happened, you have to go for the distributed control system. So both of the LC having coordination as well as all the LC. There will be no centralized control, individual controller, but they are having coordination. That we are talking about coordination control. Okay, so other very commonly used control strategies also available in the literature like group control. Now virtual oscillatory based controller also be there. Okay, so communication based control, we are talking about smart grid. Yesterday madam also talking about smart grid protection. So all those case control plays the very important key roles, and different kind of control. It's a very vast area for the control of the microgrids. Okay, so we are keeping some of the name. It's not like that everything is completed by these two slides. There is a number of different numbers of controllers also available in the literature. Based on our requirement, so we cannot select that XYZ controller for our application based on the requirement. Okay. So I hope this is my so thank you. If you are having any queries, please let us know. So we are almost first session is we are almost up to. We are going to complete our first session. We have to go for our next session. So if you are having any queries, please let us know.
Now the session is open for discussion. From any query from audience can ask to sir.
Sir, all the variations that you have taken here, that is a step variation like irradiance and those things, that is a step variation. But actual case, it is not the step, it is a
Not
gradual
step variation,
variation.
yes. Yes,
But
actually main thing is that we are having some time constant. Some of our students are working in this domain. If you follow our paper, you can also see that some of the cases we are also having real-time data for the
real
variation.
data.
Yes. So this is only for that showing the concept, how it is working. That's why we are taking some step variation. But practically, it's not a step variation. You are right.
And sir, another question, one point you said that the corner frequency of the filter that must be much less than the switching frequency. But
Due to filter. Yes, so based on that, you have to selecting the filters. So this is a basic prerequisite. Okay, for designing the filter.
what is the reason for that?
What is the
Reason for that we are
Acha,
choosing?
if you see, if you see the corner frequency and the switching frequency relation, so basically directly we are taking. If you see the one point is that it is called that system identifications. Okay. So system identification, what happen if you vary different frequency level, the transient response also being changes for the open loop system. We are going to the closed loop system, we cannot go to the closed loop system directly. If we are following the ZN method, you can able to see first we are doing the system identification, means what is the range of operations. Okay, first we have giving some of the variation of your input, then what kind of output we are getting is follow the hysteresis loop, which zone it is working. For that one, if we see it is not if it is not valid at that point, so the response will not coming properly. Okay, that's why this concept should be maintained. Okay, this is the basic from my point of view, this is the basic reason for that.
Okay, thank you, sir.
Thank you.
No?
Yes.
Sir, in your system, you have shown that one zero is in the right plane, na RHP.
Yes, yes.
So, but basically, in case of PV and boost converter, one pole is present in the one pole is usually present in the RHP.
No, no. If one pole is present in RHP, so it will be unstable system. Na? Basically, it's a basic concept of boost converter. So I am not introducing that zero. It is already there. If we do the mathematical structure, it is already coming. Zero is in RHP, right a plane. That's why
in
it's
case
the
of buck
problem.
boost converter.
Yes, boost converter, buck boost converter, and all the derived converter, boost as well as buck boost. It's having one zero in right up plane.
Okay, and but due to the PV dynamic, there is one pole in the RSP usually present, na, which we usually ignore. But so if we use both boost and buck boost converter, then what will be the difficulty? When how to design the controller? So it will be very difficult, na?
Okay, if
So
the
for
pole
that
is
case,
there,
we will have
okay,
one
one
pole
minute,
at RHP and one zero at RHP.
No, if pole is in RHP side, so there is it's an unstable system. Okay, as simple as it. So if it is unstable, so that's why maybe the reason to neglecting that pole. Okay, but I don't know. I have to see the literature. But whatever my idea is there, one RHP 0 is definitely present in the boost converter if you are considering the ESR value. Okay, ESR means if you consider the ideal condition, so it may not be present. But if you taking that non-linearities, it definitely present. Okay, so maybe the reason it can be it can be omitted, but due to the zero, there is issues of non-minimum phase. That's why we have to design.
You have considered the linear system, na sir?
That's why mathematical modeling is there. That's why we have changing the non-linear system to the LTI system, linear system.
Okay, thank you, sir.
Thank you.
Good morning, sir.
Good morning, sir.
Sir, I have a small doubt. What are the effects of parametric uncertainties in this particular design of converters, and how it affects the control?
Definitely. We are talking about sensitivity analysis, parametric uncertainties. Okay. So whatever we are doing, so basically, suppose we are designing one boost converter or buck boost converter, whatever converter we have. So whatever inductor values and capacitor values or ESR values we are considering, so we are changing their range. Okay. So means suppose we are selecting one inductor value. Practically it has not been changed, but we are considering if anyhow any situation arises due to the aging effect, that values has changed. So we are considering that plus minus 5%. Okay. So the changing of the inductor value as well as whatever values can be there, or the ESR values. Okay. With having the same controller, how the transient response is changing, that we are going to study. Okay. So from that we are able to understand the parametric uncertainty and the sensitivity of the system. Okay. As well as sometimes what happen, we are additionally some disturbances or noise also be given just input of your control, that we are talking about that error signal VE. Okay, we are adding some additional small disturbances over there. Okay, so then what happened? So if the controller is working with this situation, so we can say like that that system can be applicable for the practical studies also. Okay, by that time we are observing in computational analysis. After that, we are implementing in experimental platform.
Okay, sir. Sir, you have using one more source, more than one sources, right? So how you are considering the cross coupling between them? So
that we have not considered
load
actually.
regulation.
Cross coupling effect we have not considered actually in this study. Basically, cross coupling effect can be if you are using one transformer, okay, and it's having some multiple winding, but directly we are not considered such a way. Okay, so we are not considering this effect.
What I mean to say is between DC to DC converters, when you're designing the control, you are saying about three controllers, no, sir. One is decentralized, centralized, and distributed. So when you go
That
on
I
with
have not
centralized,
designed actually. That I have
okay,
not designed. I have just shown some slide that can be done. Centralized mode, decentralized mode, and coordination control. Okay, that can be communication between. That I have not done. We have done only some voltage mode control with classical controllers. Some of our students are working on the power management algorithms as well as their control. Okay, that we are done right now. But directly synchronizations, all those things, we are not directly we have not done till now. We are taking from the literature
because you
for.
had kept a slide, that's why I was
Yes.
asking.
Okay,
Oh,
okay.
okay, thank you, sir.
Thank you.
So I request participants, if any query, can directly mail to sir. So I would like to extend heartfelt thanks to Professor Arnab Ghosh sir for such an informative and conceptual lecture on different types of converter and its application in microgrid. Thank you so much, sir.
Thank you.
So the next session will start at 11 a.m. by Professor Munmun Khanra ma'am on the topic size of energy storage in electric vehicles.